Hello, everybody. Hey, this is going to be a review and going through assignment 10.4, which is on work and energy. You guys, this should be a review since we have gone over all this stuff. But even though it's a review, this is going to be much trickier than the first assignment on kinematics. All right, so if we look at what is being asked in the first part of this problem, we have got a block that is 10.2 kilograms, and it has a force being pushed to the right that is equal to 50 newtons. And in this first part, there's going to be no friction. So the coefficient of friction is going to be equal to 0. And this is going to end up going 4.0 meters by the end, which we will have some calculations for that. And when we do these problems, we're going to want to draw a free body diagram. And in this free body diagram, this should be a review, but you want to have, for example, a dot that is going to represent your mass, and then you want an arrow for everything that touches it, plus gravity, plus friction. So when we think about this object, we're going to have the ground. The ground is going to be touching this object. And as you will remember, that is the normal force. The normal force is going to be the perpendicular force of a surface acting on an object. We're also going to have the applied force, which is going to be, in this case, moving to the right. Now we're going to have gravity. So our force of gravity is going to be going always straight down. And you may remember that the force of gravity is equal to mg, and g is equal to 9.8. And in this case, we have no normal force, we have no friction, but friction, we will see in the next section, is going to be going opposite the motion or potential motion. Okay, so even though we do not have that yet in these first 5 problems, we will end up having a force of friction that is going to the left. All right, so now let's get to some of these problems. And we want to calculate the weight. And the weight is simply mg. The force of gravity is another way to say mg. So we're going to have 10.2 kilograms times 9.8 meters per second squared, and we're going to get 100 newtons. So that 100 newtons is the weight. And if we think about question number 2, we're going to have the sum of the forces in the y direction, the sum of the forces in the y direction going up and down. And we can just see if we have a block just sitting on the ground there, its acceleration, okay, is going to equal to 0. So remember, the sum of the forces is equal to ma, and in this case, may, and also in this case, it's not moving, so the acceleration is equal to 0. So we know that going up, force normal, minus the force of gravity, which is 100, is equal to 0. Therefore, our force normal is equal to 100 newtons. Okay, let's go ahead and start putting these answers up here on the right. So our first answer was the weight is equal to 100 newtons, and our force normal is equal to 100 newtons. And our third question, what is the acceleration of the block? What is the acceleration of the block? So for this third problem, we're going to do the sum of the forces in the x direction is going to equal to ma, and in this case, the acceleration to the x. All right, so we know that our net force going to the right is 50 newtons. So 50 newtons is going to equal to 10.2 kilograms times acceleration. We're going to divide by 10.2, and our acceleration is going to be 4.9 meters per second squared, and that is equal to our acceleration. So problem number 3, acceleration is equal to 4.9 meters per second squared. Okay, question number 4. How much work is done on the object? So you guys will remember that work is equal to force times distance, which are both vectors, which would be equal to the absolute value of force times the absolute value of displacement times the cosine of the angle between them. And we can see here that the angle between the force and the displacement is going to be 0. Cosine of 0 is +1. So we're just going to have, for this fourth problem, we're going to have 50 times 4, and that is going to give us an answer of 200 joules. Okay, so the work is equal to 200 joules. 200 joules. So we have done the first 4. Now, the last one in this segment, assuming that the initial velocity is 0, calculate the final velocity. So again, you might remember that work is going to be equal to the change in kinetic energy, So we know this net work is 200 joules, and that's going to equal to 1/2 mv final squared minus 1/2 mv initial squared. Since our initial velocity is 0, this part goes away. And we also know that our mass is 10.2. So we're going to say 200 times 2 divided by 10.2 is equal to v final squared. And then we are going to take the square root of both sides. And now we're going to say 200 times 2, not 10. So 200 times 2 divided by 10.2 is going to give us 39.2. We're going to take the square root of 39.2, and we're going to get 6.26 or 6.3. So with question number 5, our V final is equal to 6.3 meters per second. Now, you guys, that is the first 5 problems, and I'm going to erase a little bit here so that we get the room for the next calculation. All right. So now, a lot of these problems here are going to be the same, except now in this next section we are we're adding friction, and this coefficient of friction is going to equal to 0.25. Okay. So now we're in fact going to have this force of friction that is now part of that free body diagram. Since our applied force is horizontal, that means that the normal force is going to stay the same. So gravity going down, normal force going up, they're both 100, so they're equal and opposite. And we're still going to have 50 newtons to the right, which is going to be our applied force. And now we need to calculate what is the force of friction acting on the block. The force of friction, as you will remember, is equal to mu force normal. Force of friction is equal to mu force normal. We know now that our mu is 0.25, and we know our normal force is equal to 100. Therefore, our force of friction is equal to 25 newtons. Now, You guys, that is 25 newtons going to the left, and therefore it's going to be negative 25. Now we may, if you look at this equation up here, the absolute value of 100 is 100. The displacement, this is going to be work in a second here, but we know that the force of friction is going that way, and since we called to the right positive, our force of friction for question number 6 is going to be equal to negative 25. Force of friction is equal to negative 25 newtons. All right, so problem number 7. What is the work done by friction? So now the work done by friction is we are going to have 25 newtons times a distance of 4, force times distance, and that is going to be negative 25 times 4 is going to equal to negative 100 joules. Now, again, if we think about this, the absolute value of negative 25 is 25 times the absolute value of 4 is 4 times the cosine. Now, the angle between them is 180, and the cosine of 180 is negative 1. So you can kind of think of it in both ways. If you just have that relevance of you're working against friction, then the work is going to be negative. Or you can kind of do it more formally where you have that angle of 180. Okay, regardless, okay, our answer to problem number 7 is the work done by friction is equal to negative 100 joules. Problem number 8, calculate the net work done. Okay, well, we know that our overall work done by the applied force was 200 newtons, and our net work done by friction would be 100 newtons, and we just add those together. Okay, so with problem number 8, we're going to have 200 minus 100 is going to give us a net work of 100 joules. So number 8, we're going to have 100 joules is equal to our net work. Problem number 9, determine what the force is, assuming that we have an initial velocity of 0. So again, this just becomes our work is equal to our change in kinetic energy, which is 1/2 mv squared. 100, let me change colors here. Work is equal to 1/2 mv final squared minus the other one, but that's 0. Okay, so that's going to be 100, 1/2 of 10.2 v final squared. So move that half over, so we're going to get 2 times 100 divided by 10.2. We're going to take the square root of both sides, and we're going to get the final. So 200 divided by 10.2, 19.6. The square root of 19.6 is going to be 4.4. So our velocity here is 4.4. So question number 9, our V final is going to equal to 4.4 meters per second. 4.4 meters per second. All right. So you guys, that should be pretty straightforward. Very common sort of thing. What is really going to sort of change things here is if we change the angles. And one of the way we can change these angles is instead of pushing directly horizontally, we're going to push up at an angle. Now you could also be pulling up at an angle, but in this case, this next section is we're going to be pushing down on the block. All right, so let me erase this and set that up for this next part, and then we will see what's going to happen. Again, all our numbers are going to be the same, okay, except for the angle. All right, so now we're going to still have our 10.2 kilogram block. It's going to be on a horizontal surface, but now we're going to have 50 newtons. Our applied force is going to be 50 newtons, and it's going to be at an angle of 37 degrees below the horizontal. Okay, so this right here is 37 degrees below the horizontal. So notice that as this comes down here, it would sink below. All right. Now, what is particularly nice about the angle of 37 degrees is that it forms a magical 3-4-5 triangle. Okay. So problem number 10. What is the applied force in the x direction? In the x direction. And so since this 50 becomes our hypotenuse, we can say 50 cosine 37, and 50 cosine 37 is going to give us 40 newtons. And for our next question, we're going to have 50 sine 37, and that's going to give us 30 newtons. And again, if you guys recognize that that was a 3-4-5 triangle, then obviously 50, 40, 30. All right. So problem number 10 here, our force in the x direction is equal to 40 newtons. Problem number 11, our force in the y direction is equal to 30 newtons. Let's make sure we've got that. Calculate the applied force in the x, applied force in the y. Now we want to determine the normal force. Now the normal force is now changed because we're pushing down. And when we're pushing down, okay, we're essentially adding to how much the ground is having to push up. Okay. So I'm going to kind of redraw this free body diagram. Okay. And we're still going to have the force of gravity going down. We're still going to have the force normal going up. We're going to have, and this is where it changes. We're going to have our applied force in the x direction, and we're going to have our applied force in the y direction. Okay, so this applied force in the x direction is going to be 40. And this applied force in the y direction is going to be 30 newtons, okay? We know that our mg is already 100, okay? 10.2 times 9.8 is going to give us 100 newtons. And now we can see that going down is 130. Going down is 130, so we're going to have 130 going up. And that comes about from the sum of the forces in the y direction is equal to 0. Now, technically, it's equal to ma, but we know it's not going to be moving up and down, and therefore it's going to be equal to 0. So we're going to have force normal going up minus 30 minus 100 is equal to 0. We resolve that, and our normal force is equal to 130 newtons. Our normal force is equal to 130. Okay, so now we want to determine what is the coefficient. What is the coefficient of, what is the force of friction? What is the force of friction? And what we did not put on our diagram is the force of friction. And the force of friction. And that's going to equal to mu force normal. So we know that our mu is 0.25, and we now know our normal force is 130. And we calculate that. So 0.25 times 130 gives us 32.5. We're going to call that 130. We're going to call that 33. So problem number 12, our force normal was equal to 130 newtons, and our force of friction is going to be equal to 33 newtons. Now, again, we know that that's going in the negative direction. So force of friction is negative 33, negative 33. All right. What is our net force? So basically, we're going to have 40 newtons going to the right, and we're going to have 33 newtons going to the left. And that is going to give us a net force that's going to equal to 7 newtons. You guys, more formally, this comes from the sum of the forces in the x is equal to ma, and we're going to have 40 minus 33, which would give us 7. That's the sum of the forces. And in our next question, we could have asked what is the acceleration? We divide that by 10.2 and we would have had our acceleration. Okay, so what question are we on? Number 15. So our net force. Now, you guys, looking at it, our net force is really 7.5 newtons, because when we had this 33, when we did 130 times 0.25, it was 32.5. But when we put that up there, we had to round to two significant digits, so it rounded to 133. So when we go and take our 40 minus 32.5, it ends up being 7.5. So it's always good to do all your calculations and then round at the end. So if you miss that and put 7.0, it's not really that big of a deal, but technically it would be 7.5. Okay. All right, so 15. Okay, how much work is done by the applied force? Okay, so we know that work is force times distance times the cosine of the angle, okay, times the cosine of the angle. But since we've already resolved this 40, we know that 40 is going to the right, and we go to the displacement is going to the right. So that is going to be 40 times 4. So 40 times 4, and that is going to give us 160 joules. 160 joules to the right. And the next question is, how much work is done by the force of friction, which is going to be 32.5 times 4. Gives us 130, but that is going to be negative 130 joules because it's going to the left. And now it's saying, what is the network? What is the network? And we're going to add these two together, and we're going to get 17, and that would be 60 minus 130 is going to be 30 joules. 18 is going to be determine the speed. And now we can go back and use our work is equal to the change in kinetic energy. And again, our initial velocity is 0, so that's just going to be equal to 1/2 mv squared. So we have a net force, a net work of 30 is equal to 1/2 of 10.2 v final squared. So we're going to multiply both sides by 2, divide both sides by 10.2, and then take the square root, and we're going to get v final. So 60 divided by 10.2 is 5.88. Square root of 5.88 is equal to 2.425. So our v final is equal to 2.4 meters per second. 2.4 meters per second. All right, so you guys, we're almost done. All right, so now this in this last section here, we have definitely a more complicated sort of free body diagram. And that is where I want to go through this without having to answer all the questions about network and stuff. So we're just going to essentially talk about the free body diagram and how it applies, and then we'll go from there. All right, so let me erase this, and we will talk about these last two problems. All right, so you guys, now we're going to have a ramp like so, and that ramp has an angle of 25 degrees. We're still going to have our block up here, okay? And now we're going to have an applied force that's moving to the right. And again, for these purposes here, we're going to ignore friction. We're going to have a coefficient of friction that's equal to 0. So determine what the normal force is. So this, again, we can see is going to be a little bit tricky. So when we have a free body diagram, we want everything that touches it plus gravity plus friction. Now, in a free body diagram, we want to separate everything out and then draw the arrows. Sometimes it's kind of a pain. We can just put it right on top of our drawing, and if it gets too complicated, then we can separate it out. Okay, so we're just going to do that. So now we're going to have our force of gravity, okay, and now we're going to have this applied force, and we're going to have this force normal. If we had friction, okay, it could be going down, right? It could be going down if this force was high enough, right? But if this block was heavier, it could be that this force would not prevent it from coming down. And if it was not prevented from coming down, we could have our force of friction on the other side, okay? And that's why we're ignoring that for now. All right, so here's the issue. We want to take all of our forces and resolve them into our XY coordinate system. But because this block is on a ramp, we're going to make up and down the block in the X direction, and we're going to make that perpendicular in the Y direction, right? So we've essentially just changed what our XY coordinate system is. And that will make things easier when this thing actually moves, because then we only need one calculation instead of two. All right, so we can see that our normal force would be in our Y direction, but our applied force is going partially in the X direction and partially in the Y direction. Okay, so since we know that this applied force is still equal to 50, and this angle is 25 degrees, in order to determine that force of that component in the X direction, that's going to be 50 cosine 25. So 50 cosine 25 is 45.3. So we're going to say 45.3. And we're going to say 50 sine 25. And that's going to give us 21.1 newtons. That's going in this direction. All right, let's change colors here. Now, this force of gravity is not acting in the X or Y direction, so we need to break this one down, okay? So that's going to break down into this direction and this direction. So this side is going to be mg cosine 25 degrees. Guys, if this is 25 degrees, that's 25 degrees, and this is 25 degrees. And if you just think about that from a geometric point of view, you'll arrive at that result of this angle being 25 degrees. And so when we talk about this one, this is going to be mg sine 25 degrees. Okay, so we know that this is going to be equal to 100. 10.2 times 9.8 is 100 times the cosine of 25. 100 times cosine of 25. And that's going to give us 90.6. Okay. And that's going to give us 90.6. We'll call that 91 newtons. Okay. So we're going to have 91 newtons going this way. And then this one is going to be 100 times the sine of 25. And that's going to be 42.3, which we'll call that 43 newtons down the ramp. 43 newtons down the ramp. Okay, so now we need to figure out what our normal force is for this question. So I'm going to kind of talk about it down here. Force normal is going up like this, and the component due to gravity that's opposite of that is 91 newtons. The component of the applied force is going to be 21 newtons, which means we're going to have a total net force down or into the ramp of 112, and therefore our normal force is equal to 112 newtons. So problem number 19, force normal is equal to 112 newtons. All right, and our last question here. What is the net force acting up the ramp on the block? Okay, so we already know that going up the ramp was 45.3, and going down the ramp here was, I believe, 42.3. I'm going to change that back into 42.3, and we're going to take up the ramp 45.3, down the ramp going 42.3, and therefore we're going to have a net force of 3 newtons, okay, which is 45.3 minus 42.3, and that's going to equal to 3 newtons. Our net work up the ramp, force net, is going to equal to 3.0 newtons. All right, so again, we could expand on this and we could talk about what if the force of friction times this normal force would give us that answer. We could talk about how far the object went to calculate how much work was done, and we could go on and on. But I think you guys kind of get the idea. All right, so there is all of your answers for this next assignment, which is reviewing work and energy as it comes to objects being pushed on the ground or up a ramp. All right, until next time, we'll see you guys later.